All right, so welcome everyone. Today we have Quan Nguyen, who's joining us from USC. He did his graduate work at Carnegie Mellon, where he actually won the Best Dissertation Award and actually worked with an alum of Michigan. And so, in fact, Quan is like a grandson of Michigan. And today he'll be talking about some of his excellent work as a grandson of Michigan, working on, would you believe it, walking robots. He's going to show you all sorts of incredible stuff. And so please join me in welcoming Quan.
Okay, thanks, Ram. Thank you so much for inviting me, and it's my great pleasure to be here today. And as Ram mentioned, Michigan is always a very special place to me because, Jesse Grizzo is my academic grandfather, so I always look up to Michigan. It's very honored to be here today. So today I'm very excited to present to you our research on hierarchical optimization-based control for Agile and adaptive legged robots. And during this presentation, if you have any questions, feel free to interrupt me at any time. Okay. And this is one of the videos I would like to show you to talk about the motivation of our research in general. And I'm feeling very happy and very lucky that I could find this video, because later on you will see that it's very relevant to what I will be presenting today. So let me play the videos, and along the way I will try to explain what is happening here. So this is a video of the competition of the firefighter. I'm sorry about the quality of the video because it's post over Zoom, so it's a bit of choppy. However, as you see here, there's several things that I want to highlight in this video. As you see, this firefighter always need to deal with a lot of combination between locomotion and manipulation. So what I'm trying to talk in this talk is that how can we combine using the entire body to do locomotion and manipulation. I have no idea what they are doing here, but the second part will be more interesting. So they run around, it's never walk actually, they keep running, do everything as fast as possible, right? And as you see here, they try to combine between locomotion to support this manipulation task. So that is one thing I want to highlight. And here is also an interesting problem, as you see, is lift up this very heavy object, I would say, human subject, and it's trying to carry it around. And as you see here, if you have our robot recently, if you just simply pick up this object and move around, it's not simple, right? So you need to really leverage the entire body motion to support this. So several key items that I want to highlight here. So as you see in the video, we can see that, okay, humans really do dynamic whole body local manipulation. So what is the meaning of local manipulation? Here, I use this term to represent when we really need to combine locomotion and manipulation at the same time, right? And you will also see that, okay, they really adapt to the load carrying problem and also adapt to a lot of challenging terrains. And these three are actually the three main research problem that I will try to address in this talk as well. Okay, so as you see, hopefully from the video, it gives you some idea that, okay, legged robot is kind of helpful, right? If you can get to the level of, human mobility, I believe that legged robot can be, helpful in many meaningful application, from disaster response, firefighting, construction industry, or supply exploration, and many more. Okay, so I think for this kind of application, in my opinion, there's two main things that we might want to, get for the legged robot if you want to get to this level is not only agility, right? Many people talk about agility, but I think in my opinion, adaptation is also very important. So to work on this direction in order to, let me see, I can hide this. Okay, so in order to work on the direction so that we can really achieve high agility and adaptability for Lego drivers. These are 4 research directions that I will be presenting today. So we will talk about, and I also have several videos that highlight the research direction that I will be talking today. Okay, so let me show you a couple of the video. So here on the corner here, you will see this humanoid robot picking up the box, moving it very quickly. And this is a problem of dynamic locomotion, and we will try to use MPC for this problem. In the second video here, so we'll see this robot running very quickly when it needs to carry a very heavy load here. So load is unknown to the robot. So in this problem, I will talk about adaptive control for Lego robots. And for this third video here, as you see, we have the problem of quadruped robot running on stepping stone, but this also uneven stepping stone when the high variation is changed and it's not given to the controller. So in order to achieve this kind of robust and dynamic motion, we propose to combine between MPC and trajectory optimization for this talk. So this will be the third topic that I will try to present today. And in the last one, hopefully the video will play well. I'm not sure if I can try to play it again. Yeah, so in this video, I want to show that an interesting kind of adaptive behavior when the robot try to lift up the foot when it climb up this stair blindly. So there's no vision system happened here. It's blind locomotion, and we try to use reinforcement learning in combination with MPC so that we can achieve this adaptive behavior. Okay, so hopefully this gives you a big picture of what I'm trying to mention today. Okay, so before moving on to explain better the motivation of our research, I would like to give a quick background on control of Lego robots. And we cannot miss hybrid zero dynamics. Okay, this is a very nice approach. It's applied to many different approaches here. We have bipedal running, we have humanoid robot walking, we have prosthetic leg control here. Okay, so this is a very nice approach. So I will not touch this approach for today's talk. Okay, so please allow me to move on and then talk about a second kind of trend or control approach for Lego robots. So this is primarily designed for Lego robots, for quadruped robots. Okay, so we have MPC for Lego robots. So this is introduced very recently, it's about several years ago. And as you see here in this video, the robot climbs this stair. So let me play this video. And as you and this is totally blind. So no camera, no prior information about the terrain. This MPC controller working very robustly in this terrain problem. Okay. So for this approach, the advantage of this is that it's very robust to uneven terrains. And there's another part that I did not show in the video, that with basically the same controllers, you can adapt to many different gates and many different velocity commands. So it's very generalizable. So one single framework, but it's worked pretty well. However, the question is, what is the disadvantage of this approach? So in order to better explain what is the kind of disadvantages of this approach and how we want to expand in our research, let me try to give you a very brief idea on what is the background on this approach. Okay, so in this framework, as you see here, we have the combination between two main different terms. We have MPC force control, and then we have swing foot placement control. So basically two controllers working together at the same time. So it's more like a hybrid control system. Okay. So for the role of the MPC force control here is that we designed an MPC controller so that we can optimize for the gravitation forces at the standpoint. So let's say it's a robot. We have the gravitation force between the robot and the ground. So the MPC controller will try to optimize for this interaction force. And the model that is used is a simple single rigid body dynamics. And I will explain about this model later. But basically the idea that in order to allow the MPC controller to run in real time, right? You want to have a more simplified model for this. And yeah, again, this allows you to formulate the MPC controller as a linear model predictive controller formulation. Okay, and the second part here is a swing foot placement. So as you see, the swing foot means that, okay, when you have the stand foot on the ground, but in order to have the robot keep moving, you cannot just keep the 2 foot on the ground all the time, okay? You need to lift it up, move to the next step. So this is part of the swing foot placement controller that you need to have. Okay, so let's move on to explain the single rigid body dynamics. So basically here, what we have that we consider the dynamics of the robot as a single rigid body. So what does that mean? So it means that we ignore the dynamics of the legs. We assume that the mass of the leg is, significantly smaller than what we have on the trunk. So I know that this is a simplification, okay? But this allows us to capture what is the main kind of contribution of the gravitational force to the robot body. And a nice thing that we have this linear model here, okay? And because of the linear model, you can formulate this as an MPC formulation using the linear model. You simulate the model over and over again for many iterations over time, and you put it in the MPC formulation. And the nice thing here that is the linear formulation, okay? So in this MPC formulation, there's several kind of main parts that I want to explain here. So for the cost function, the main part is that you want to track the desired reference. So what does that mean? So for example, you have the robot here. You want to command or control the robot like you are playing the video game, okay? You send a certain input command. The MPC formulation will try to track this desired reference, okay? And the second part here is also very important. You want to minimize the control input to minimize the energy consumption, okay? So this is the role of this kind of the second term here is not only really help you to minimize the control input or energy, but it's also very important to guarantee that you have a feasible solution for the optimization problem. Okay, and then you have this dynamics here, and there's several constraints. So the first one is representing the linear dynamics that we mentioned earlier. The second part is also very important. You want to mention friction constraints in locomotion. And in locomotion, it's very important because when it slips, right, basically it screw up everything. So this is a very important constraint as well. Okay, and you also have the force constraint. So what does that mean? So this is also important because when you have the force on the ground, you cannot push in the negative direction, okay? The force always need to be in the positive direction. Okay, so in order to better illustrate, what the benefit of MPC in this motion, in this problem, let me give you a very simple example. Let's say you have simplified the problem a bit. We have 2D quadruped robot. It's now biped, but it's a different type of biped, okay? And because in the MPC problem, we only consider, the single rigid body dynamics, right? But here, as you see, is only one stand legs here. So we only have one gravitational force on the left foot here. And because this is swing, okay? So because of that, the gravitational force becomes 0. So you don't have any control input for the gravitational force. And the role of the MPC controller is that we would try to simulate this motion over time and make the decision based on this kind of prediction. So let's say it's this is basically it's need to run a lot of different simulation, but let's say this is a final result, for example, okay? It's make the decision on what would be the next position and orientation of the body. What is the gravitational force that you need to apply in the next iteration? It's repeating it. Let's say third integration, fourth integration, and the fifth one. Okay. And now let me stop here a bit. So as you see here, I make a slightly different color for this one. So the emphasize here that at this point in the middle of the gate, okay, you might want to switch between swing and stand. So let's say here, you expect that you may move between, okay, the front foot here now becomes sweep. Okay, so because of that, at this iteration, you no longer, you will switch between, okay, rear reaction force here to front reaction force you want to optimize. Okay, and you, okay, go ahead.
Are you assuming that the legs have zero inertia?
Yeah, so that is a assumption for the single rigid body dynamics that we have for, in terms of the dynamic we use for MPC. Yeah.
Right. Picture.
Yeah, as I mentioned earlier, I know that this is not the best way we model for, to have an accurate model for legged robot, right? But this is really helpful in terms of, simplify the computation for the MPC. Yeah, and actually this is also a kind of an disadvantage of MPC. And later on, when we expand more for, let's say, more aggressive motion like jumping, we really need to explore the leg motion because now the entire body moves very quickly. So I will also talk about the combination between, let's say, trajectory optimization when you leverage the entire body dynamics and this simplified MPC formulation. Okay. Any other question before I move on? Okay. Yeah, so let me keep explaining this. So as you see here, we switch to this front force here now because we switch between rear contact to front contact. Okay, so we change this, but then you keep formulating forward the simulation here. Sorry. You will see that there's some expectation at the end. Okay, so let's say if you do the control problem properly, you will be able to kind of move the robot in a certain direction that you want. Okay, you keep the body orientation kind of in a certain range that you want. Okay, one thing that you can keep in mind here that as you see here, if you only have kind of rear leg contact only, it's not possible for you to, sorry, let me go to this direction, right? If you have the force direction here, right, as you see here, the pitch angle on way going down, right? Because you have force this way. If you want to going up this way, it's not easy, okay? So this, because thanks to this kind of contact sequence embedded in the MPC controller, you have the constraints of the force for the entire kind of horizon in the prediction horizon of the MPC. Okay, so without having this, I think, let's say if you desire a control problem in general and you think that, you can apply any arbitrary control input, okay, you can just simply have this body running very flat on this way, right? But in bounding, because you have some constraint in the control input, let's say if you have rear leg contact, it's bound this way, front leg contact is bound this way. So you need to switch between them, okay? But with the MPC formulation, because you have the prediction for the entire gate, you basically can simulate and apply this constraint for the entire horizon. Okay, and first, as I mentioned, the second part of these controllers is also the swing control. And so this is formulation for the swing control. I will not try to explain it in detail, but as you see the principle here that this kind of footstep in the future, okay, it's kind of depend on the current velocity, okay, and the desired velocity that you want to have in the future. So there's two main roles for this. Is basically, let's say if you're standing still, and if you get some disturbance from outside, you will try to react to it. Okay, or let's say if you want to speed up, right? So let's say what the current velocity is 0, you want to speed up gradually to catch up with the desired velocity that you want to have. However, as you see here, there's not really any relationship between swing control and MPC force control that we have. Okay. So hopefully from the background of MPC for legged robots, I can somehow convince there's several, the disadvantages of this framework. And I would like to show the solution that we have corresponding to this disadvantage. So the first one, as you see, is mainly designed for quadruped locomotion. So here in the first part of the talk, I will talk about how we expand it for, the problem of local manipulation and also for humanoid control. Do you have any question?
Yeah, just a quick question. When you showed the robot and you said it's hard to increase pitch, if you assume that the front legs have inertia, wouldn't that help you at the expense of a worse model?
I would say that not much.
Really?
Okay. Let's say, I think it depends. So let's say for humanoid, when you have a heavier, let's say legs inertia, it may help a bit, but for most of the quadruped robot designs, the leg is very light. And no matter how hard you try to swing the leg mid-air, I think the contribution is very small. Okay. But I mean, even with humanoids, when the leg is heavier, the inertia is higher. You can try to swing it a bit, but if you rely on it too much, I think it's not really good for the stability of the system in general. Okay. And the second part is, as we discussed, that is also based on the simplified model. When it's necessary to make sure that the MPC controller can be solved in real time. Okay, but when we move on to adaptation to model uncertainty, for example, in the first video when I show you, the human need to drag another human. Okay, it's a very heavy lifting problem. So we need to, the model uncertainty in the dynamics of the entire system is pretty significant. So we want to develop an adaptive control for this. And a third kind of limitation for this is that because, as I mentioned, during the MPC formulation, you want to capture the entire gait. So basically, if you have a flight times, so let's say you want to run with a very high flight time, long flight time, you need to capture the entire motion. Okay. However, if you capture the entire motion and if this time is long, it's not possible for you to capture all. Okay. So if we have long flight times, our solution is that we want to combine between trajectory optimization and MPC so that we can address this problem. And the last one is that, as I mentioned, we have two control blocks. One is MPC, one is swing control, but there's no interconnection between them. So in order to better investigate what is the connection between them, we try to study how to use reinforcement learning in combination with MPC so that we can explore this kind of behavior. Okay. And this, let me try to go back to this. So this is 4 solutions related to this 4 disadvantages that I'm trying to convince. And this is actually the 4 topics that I will be presenting today. So hopefully it's give you a big picture about this. So let me move on to the first topic when I talk about local manipulation for legged robots. How can we expand from MPC for quadruped robot for this problem? So the vision that we have in this kind of research direction, that there are 3 main problems that we are trying to address here. Right? The first one is how can you basically leverage the whole body motion so that you can do locomotion and manipulation smoothly at the same time. Right? It's not like you move to a certain location to pick up an object and move it around. Okay, you want to do it in a very effective way. And that's in local manipulation, there's 2 different things. It's not only the interaction force or the manipulation force that you want to do, but I think the contact location is also very important. And the last one I will present in the next section is related to adaptive control. Okay, so for this kind of the first section, there's 3 main problems that or projects that I will be presenting. The first one is to let's say if you have a heavy object here, okay, you have a legged robot, you want to move it around. How can you design the controller to make it happen? Okay, so let me present the first one. And let me briefly talk about this different direction here first. Okay, and the second topic I will talk about how we expand this MPC controller for humanoids and how can we address the problem of, let's say, dynamic walking on stepping stone. And the third one is locomotion, local manipulation for humanoid robots. Okay, so for the first one, this is the control diagram for this problem. I will just highlight some key ideas here. But as you see here, for this problem, when the robot needs to push this box around, there are two kind of control decisions that you want to make, right? You need to make the decision in terms of what would be the interaction force that you want to apply to push it, and also the contact location. And later on, you will see some of the video on how this makes it's change the contact location during this task. Okay, so for the first one on contact optimization, as you see here, let's say this is top view from the robot. This is an object. Let's say this is the center of mass of the object. So you want to control the contact force is one thing, but you also want to, let's say, control the contact location, which is represented by this distance d here. Okay. And in order to optimize for this, we designed another layer of MPC. So this is not the MPC controller that we use for locomotion. This is another layer of kind of contact optimization on MPC. And this gives a very simple dynamics of this object with the control variables is the FC here and distance D here. So F mu here is the friction force applied to the robot. Sorry, to the object. Okay. And here we want to have an MPC formulation so that we want to maintain the contact location to be within this box size. As you see here, there's some constraint of the box size, right? If you move far away outside the box, it's not possible for you to complete this. And again, this FC here guarantee that you always have contact in the positive direction with the box. Okay. But an interesting thing here that I want to highlight is that for this contact optimizer, we not only optimize for one single like ahead of time, we run the MPC so that we can optimize a contact sequence. Okay, so we have D1, D2, D3 over time. Okay, and I think this is also important so that we can make the connection in the second part here. Okay, go ahead.
You make some assumptions on the coefficient of friction of the surface that you're moving against.
Yeah, that's a good question. In this particular project, we have the assumption on this. In the next one, when I will present on adaptive control, we don't. Okay, but for this one, we developed this based on the assumption that okay, we have assumption about the mass of the object, the friction coefficient. Okay, but then we'll build up from this and do adaptive control for this problem. Okay, so related to the first one, because we kind of optimize for, let's say, contact location and contact force, basically for a certain horizon ahead of time using MPC. Now they have an input for this for the local manipulation controller so that you can regulate this desired contact force and contact location, but not for the instant, I mean the future instant ahead of time, but for the entire horizon. And I think that's important because when you have a two complex problem you want to deal with at the same time, locomotion is already pretty complicated. Now you have manipulation. So without this prediction ahead of time, we already tried something like, okay, from the previous contact optimization, if we only try to regulate what happened in the first iteration, it failed. Okay, and I think it's very important because it has the prediction ahead of time. And for the local manipulation MPC, similar to the MPC controller for locomotion that I presented earlier, the key difference here that we have this FC here applied from the robot. So now you will need to kind of keep this in the dynamics here of the robot so that you can regulate this force applied to the box here. Okay, but again, we need to do this for not only F1 in the future, but F1, F2, Fn, I mean, in the future predictions. Okay, go ahead.
G is the gravity.
Fg is gravity. Yes. Okay. You may not have it in 2D, but I mean, this, I think this FG is on, sorry. Just want to clarify, this is dynamics of this robot, not for the box. Okay. So that's why you have FG vector. Okay. So again, the role of this MPC controller is to regulate this gravitational force in the future, but also for the contact point that we have from this contact optimization. Okay. And we have this result. So we compare between baseline locomotion. So what's the baseline? So it means that you simply apply the MPC controller that you have for locomotion and just try to manually control the robot. And you hope that you can manipulate the box, okay? But this is not simple because you don't have any feedback. The robot just roll around and you don't have any control of it. So a better way to do it could be you have this MPC controller, but then you try to make adjustments, steer the robot in the lateral direction. Let's say you have simple PD controller. You try to control it so that you can drag this robot to this location. It's similar like you drive a car by yourself, right? But the problem with this is because you're trying very hard to control the orientation, right? Is you lose the control in the position direction. And at the end, it's not possible for you to control both of them at the same time, okay? However, with the MPC controller built-in, you will see that the robot will try to gradually either push the box or move the contact location gradually so that it can track both position and orientation of the box at the same time. Okay. And as I mentioned earlier, I think the interconnection between two layers of MPC is very important to complete this task. Okay, and we put it on the real hardware, and I think it's look very similar, but I just want to show you here because I think it's maybe clear in this video that you see that sometimes the robot will try to adjust the contact location pretty aggressively. Okay, and I hope that this video will show you why we want to use the entire body to do manipulation, because if you have a robot arm, it's not possible to grab it, okay? And we expand this a bit further when we have collision avoidance with this local manipulation problem, because now you have an MPC framework, so it's kind of straightforward to expand. But we try to make the problem is pretty tricky when the goal is very close to the obstacle, so that you need to steer it around. Okay. So let me move on to the second part so that we can expand it for bipedal robot and then humanoid. So MPC is pretty nice framework for quadruped robots. So our question is that why not expanding it for bipedal robot? Okay. So I think the control system that we have here is pretty much similar to quadruped robot. We have swing leg control. We have MPC here. I think the only key difference here is what is the ideal dynamics model for MPC. Okay. So we kind of investigate different dynamic representations that we can do for MPC. I think the most straightforward kind of model that we think when we expand directly from quadruped robot for biped is that for biped, basically for quadruped robot, basically you have 4 points, right? Here you can just simply assume that, okay, you have 2 contact points here. You have a vector of 3 gravitational force. So this is the most, close model to quadruped robot that we have, okay? And then the second model is that, okay, we can keep 1 contact here, but we apply, moment in different direction. So that's the second model that we test. But then actually this is a final choice that we have. This is actually more simple than the second one, okay? But I think one of the main kind of intuition why the second model is work better because our lab have 5 degrees of freedom, okay? So we have 5 degrees of freedom left, so this seems to match better to our configuration. We can really control this 5D vector of force and moments. So we expand this for force and moment based MPC. For bipedal robots, we was able to show this in experiment. Hopefully you can see this here. So this is a mini biped in our lab. We just built it. It's pretty convenient to run experiment. We can bring it outside. So this is to test the robustness of the formula of the control problem because this ground is actually a wet and soft ground. So we just use the same controller, put it outside, test this, see what happens. Okay. We also build a mini humanoid. Yeah, my student convinced me very hard that they want to put this shirt on for the humanoid. Okay, so this controller, actually, I haven't presented the method behind it, but because I'm talking about this robot here, so let me show you first. And then later on, when we talk about loco-manipulation, I will explain this methods later. But as you see here, this also shows the, the strength of the robot. This can do squatting pretty effectively. Okay. Yeah, so just want to give another introduction here. So this is a robot that we have. We call this Hector, humanoid for enhanced control and open source research. So we try to keep the simulation open source here. So if you want to play around, feel free to take a look. If you want to get a copy of the robot, let us know. Okay, we are trying to make it happen so that we can expand research in humanoid faster and faster in the future, hopefully. Okay. And for the next topic that I want to expand it from here, that's so, okay, we have MPC for humanoid. I used to work on stepping stone. So the question for my student that can we expand it for stepping stone problem? Okay. So here we have our work on adaptive frequency and trajectory optimization. So let me try to explain why we need adaptive frequency here. So basically what we have in the previous formulation is that we have MPC, we have fixed stepping sequence. So basically you're stepping with the same frequency all the time, okay? But now let's say if you have stepping stone, obviously you cannot have the freedom to stepping, anywhere that you want, right? You have a certain location you want to step on. So for the conventional approach, because the step length depend on the gate timing, right? Now, because you have a fixed step length, so what's the solution? Simply we vary the gate frequency, okay? But it's not that simple, okay? So in order to vary the step frequency, because what we are trying to do here that we want to, make it happen in dynamic walking at high speed, there's some relationship between, the desired motion that you want to achieve and, the step frequency. So that's why we need to run another optimization, trajectory optimization here, so that we can find out what would be the optimal relationship between them. Okay. And here, because we are kind of combined with MPC, so an interesting kind of property that we can have is that you have dynamic walking on stepping stone, but it's also robust to terrain perturbation here. Okay. So this is another crazy diagram, but let me try to explain some key feature here, okay? So the first part in this kind of method that we want to use trajectory optimization. So one of the key reasons why we want to use, you need to use this because there's so when you change the gate frequency, okay? Basically the entire dynamics change drastically. So you cannot just simply use MPC to optimize for the gate frequency. It's too much for the computation. So you need to run another, even with this simple model, you need to run an offline optimization to optimize for the kind of the stepping sequence that you want to have. And then once you have this desired frequency that you want to have, you will try to design an MPC controller with respect to this kind of time varying frequency that you have in mind. Okay, and both this adaptive frequency MPC and this optimization is designed based on this simple model that we have. Okay, and this is the results that we have. So before playing the video, let me kind of emphasize a bit. As you see here, even with having this navigating on the stepping stone here, but it strikes the desired velocity pretty well. And here is about 0.5 meter per second. For this mini size robot, I think it's pretty fast. Okay. So before I play the video, let me warn you a bit. It's faster than you should expect. Okay. Ready? We cannot even see it clearly from Zoom because there's some kind of delay here. Let me try one more time. Okay. I don't think that it can play on the bed. Okay. But let me try to show you the slow motion video. So this 4 times slower. Okay. Can you see it now? Okay. So I know that this is simulation only, right? Always, want to run everything in experiment to show you, but just want to give you, a better perspective that our simulation is actually a very high fidelity simulation. So we have all the physics built in, as long as we can simulate or measure or constrain any physical parameter inside, we put everything in, right? So most of the experiment that we have previously is very close to the simulation that we have. Okay. And as I mentioned earlier, because of the MPC, we can also have perturbation on the terrain here. So here we have the high perturbation. It's not given to the controller. Okay. The controllers only know what is the desired step length ahead of time that is need to step on. Here we have the slow perturbation that is happening. This is slow motion, so don't worry, you can see it. Okay. And let's say it's a second. I think from this second video, you can see very clearly that this robot tried to kind of adapt the ankle motion with respect to this terrain. And this totally, adapt by the nature of the MPC controller. Okay, so let me start more with this multi-contact MPC. So we expanded further for the problem of whole body manipulation, as I mentioned earlier. So let me play this video so that we can see what we are trying to do here. So we have this robot. We throw this object very dynamically. So this is 2 kilograms of object. So for this robot, it's not, easy, right? I think, and the main principle of this is that we want to, so we have this model, okay? And we consider the object dynamic inside this model. But another important part that we have here that we consider the contact sequence when we perform this local manipulation task. So basically, when you pick up an object, you have this contact prediction inside. When you throw it, you have that prediction happen inside. Because as you see, the dynamics of the robot or the system, when you pick up this object and when you release it, there are 2 different dynamics that you need to switch between them. Okay, for the interest of time, let me skip this a bit. Sorry, let me play this video. So for this one, let's say even this is our approach, but just want to show you that normally people would perform quasi-static motion, right? You pick up the object, you lift it up, and you do locomotion. Okay, and now what we're trying to do here that we want to do it everything at the same time. So let me place this again here. So you pick up the box, you move this and put it down. And just want to give you a better idea that we don't have any command in what is the desired yaw for the whole body. Okay, we only ask the robot, okay, pick the box here, put it here. The desired destination is totally defined by the MPC control. Okay, and as you see here, it's saved pretty, big chunk in the ratio part, right? And if you see that if the robot need to manipulate, let's say, thousands of boxes, I think it saves a lot of time. Okay. Okay, so what are summaries that we have here for this kind of section here? So there's several kind of takeaways that I want to kind of emphasize here. So it means that with MPC or several problems that you work on, more accurate model doesn't mean that you have a better solution, right? Because I think eventually the accuracy comes from the optimization solution that is really matter. So how can you design the problem in a better way for the optimization to solve it? I think it's also a pretty good problem to address. And I think different complex tasks can be decomposed into different control layers. And as you see here, the problem of local manipulation can be decoupled to between locomotion and manipulation. But the question is, how can we integrate them effectively, right? And yeah, I think solution using optimization-based control with a different hierarchical level can deal with this object pretty well. I know that I still have a lot of going on, but let me try to skip this very quickly. Okay. So for this, the second part about adaptive control, what we are trying to achieve here that let's say if you have heavy object that you need to deal with, when you carry it, when you push it, when you do collaboration between multiple robots in the team, it's obviously the dynamics of the object here is unknown to the robot, right? And as I mentioned earlier, for this local manipulation task, the object, the friction, and here in this setup, the slope of the terrain is also unknown to the robot. So how can we design the controller for this? So I used to work on L1 adaptive control for legged robot as well. So it has some advantage, but because all of this designed for position control. But as I discussed earlier, all the work that we do MPC is for force control. So how can we kind of expand it? So one disadvantage for the position control is that we need different trajectory for different motion. For MPC, let's say you send different command, you have one single controller to handle it. So let me skip this. So the main principle that we have here that you have a force-based control is a MPC or different type of controller. You build a reference model here, okay? And this is kind of the principle of model reference adaptive control. So you compare the difference between the real robot and let's say the reference in simulation. You compare them and you design adaptation law so that you can have an adaptive controller so that you can compensate for this model uncertainty. Okay. And another important part that I want to highlight here that because in the force control, we have two different control layers, right? One force control, one swing control. So in order to kind of synchronize between the real model and the reference model, we would like to send the actual foot position measurement to this reference model. So I think this is also a key idea that helps us to expand. Another slide that I may need to skip here for the interest of time is that when we apply this for adaptive MPC, it's not straightforward because the problem here that the entire block here with a different control model, actually you need to run it everything on board. Okay, you have one MPC controller running for the locomotion. You have this reference model MPC running at the same time. You have this adaptation law running at the same time. So basically, the computation increased significantly. So here, in order to make it happen, we need to, our solution is to run this MPC in a different kind of frequency. So we certify a bit the accuracy of the reference model, but this allows us to run everything in real time. Okay, and so having this, we have this conventional MPC field, but with our adaptive controller, we can have the robot working with up to 5 kilograms of load. Okay, let me skip this. One interesting experiment that we have that intentionally we don't even think about this experiment ahead of time, right? But then we have this adaptive control. I just asked my student to see what happened if you put this robot on this form. Okay, it's turned out that this adaptive very well to this terrain, and you see here the tracking is almost perfect here. Okay, and we also tested for multiple terrains. One interesting video that I want to show here that you will see in, I think I showed this earlier, but this robot will gradually speed up very quickly when it carry up to 5 kilograms of load. And as I mentioned earlier, with MPC, we can have the same controller, but we can achieve a wide variety of different gates with the same controller. So we are expanded for bounding as well. Okay, so for and again we expanded for local manipulation when we have hierarchical adaptive control. We adapt it to the problem of manipulation here. So in this problem, the object is basically unknown to the control system. How can you adapt to this unknown parameters that we have? Okay. So just want to skip this a bit so that I can show a bit of the prism. How many minutes do I have?
So you have until 4:30, but you may want to leave a few minutes for questions.
Okay, sure. That's so good. So let me show this one and maybe. Yeah, so as you see here, this kind of load is unknown to the system, but we can adapt to it as well. So let me skip this. I think I already showed its result, but as you see here, there's no object. The contact immediately happen, and then the robot adapt to it immediately. Yeah, another interesting direction that we are expanding is that we expanded for collaborative manipulation, local manipulation. So here you not only adapt to this unknown object, but what happens if you have, let's say, multiple robots working together? And let's say sometimes you need 2 robots, sometimes you need 3 robots, right? How can you design a framework so that this can automatically adapt to this well? Yeah, so on the left here, we have some comparison with baseline, and then this proposed QP controller can handle it well. Okay. So let me see. Yeah, this is another example where I show that, okay, this is 2 different robots working together, but sometimes it's task is too tricky. You may have another team joining, and so the entire framework try automatically adapt to it. Okay, I think let me see. Is there anything else that I should show? I still have several things to show, but I think yeah, that's fine. So let maybe one last thing that I want to show. So as I mentioned earlier, when we also kind of, not sure if I can stop this. Okay. Let's see if I can play this. I don't think that is play well in this video, but anyway. So I think when we combine this RL and MPC, our hope is that we can improve not only agility, but some adaptation happen. And I think I already showed you this video earlier, but one more slide that I want to show, I think is also pretty interesting, is that because in our framework, we have this kind of scale between different robots here. So we can achieve actually zero shot sim to real transfer, not only to one single robot, but to multiple robots. So in simulation, we train, or in training, we only train for this robot, okay? But then we can transfer it to this robot well, but also to different robot. And this one is actually, twice heavier than this one. But I think the interesting part, because instead of command the force directly, right, we have this acceleration term to better represent, the generalizability for different robots. Okay, so I think that's all I have. I would like to thank all my students and sponsor for all the work here. I'm happy to answer any question that you have. Okay, go ahead.
And so with the last part, with the RL, what are you actually learning with your RL part?
Okay, I think we have a bit of more time to explain it now. Okay, okay. So here, what we are, so as I mentioned earlier in the motivation part, so what we are trying to do here is that how can we basically better integrate between force control and swing control. So what we are trying to learn here that it compensates for this dynamic compensation. In order to better explain it, I need to write out all the equation. But let's say in the MPC form, you will try to learn that there's some kind of, let's say if you treat the model uncertainty or the kind of the unknown representation in simulation using some acceleration term, you can represent well what happened. Let's say if you have the load, you have some kind of disturbance outside, and you can represent basically model uncertainty happen between simulation and experiment, and you learn to compensate for it. So that, and this kind of acceleration term also plays two different roles, right? Either you compensate, let's say if you have the load here, you can compensate for it. And the first part is, let's say, if there's some kind of dynamic motion, sorry. This one, for example, if you need to steer very fast, right? Normally the MPC controller kind of limited because you try to command the velocity, not the acceleration, right? So now if you learn to kind of command the acceleration, you will try to control the robot in the better way. Okay, go ahead.
I think someone asked on Zoom before me, so.
Yeah, I think if you click on this other machine,
Okay.
or maybe you'll be able to see it on chat or that. Yeah.
It's a pretty long question. The first one is for the local manipulation problem. Do the resultant augmented dynamics still stay linear? Yes, so I think that's a great question. So I did not have time to, oh, it showed up here. That's good. I did not have time to explain it, but we also investigate different model for this. So let's say if you have a box here, right? I think the most straightforward way to consider is that, okay, you put the box, you merge with the mass of the robot, you consider the entire body as a single rigid body dynamics, okay? But the problem is that because, let's say if you pick up the box, you have another center of mass location, you leave it out, you have another center of mass location. And it's basically inside the MPC controller, you will screw up, the computation very significantly, okay? And what we're trying to have that, okay, we're trying to represent the model in a more simple way. We consider the box as an external force applied to the system. So when you do this, we keep the same center of mass of robot. When you switch between one box, two box, zero box, it's say the same model, but a different gravitation force applied. So when you have this model, there's two benefits. The model still stays linear. Okay, so I just answers the question that you have here. And the second part that is have a gradual change. Basically, it's have no change in the formulation of the MPC when you switch between variable. let's say the second question is for L1 adaptive control. Is there any way to remove the predefined footstep location assumption? Okay, just to clarify it, there's no predefined footstep location. So the swing control will try to define the footstep location reactively, okay, based on the current velocity that the robot has. So that's the reason why I mentioned that, because that's controller also, very important to keep the robot stable. Because let's say if you're standing, you get pushed, you need to step to the right, for example, okay, and that is reactive. So you need to get the feedback control. So that's the reason why if you do adaptive control and if you're not aware of that reaction in another control layer, it's not good for you. So that's why we try to synchronize what happened in real robot to the reference model.
I think it's 4:30 at the moment, so maybe we can pause for now and thank Quan again. If anyone has any questions, Quan's around for a little while longer, they can stack some of the time.
Yeah, so this is a try. I was kept too optimistic about what I can present. Okay. Okay. Yeah, sure.
Yeah.